In this video, we'll look at the basics of right triangle trigonometry. So to start, I'm going to draw a right triangle, and we're going to call the sides various things and consider the three angles that make it up. So first thing, of course, it's a right triangle. So I've got a right angle here. And then the two segments that are next to the right angle are called the legs of the triangle, and then the side that's sort of across from the right angle is called the hypotenuse. So this one is the hypotenuse, and that's a Greek word. And what exactly we call the two legs depends on which angle we're interested in. So I'm going to be interested right now, let's say with this angle here, and typically we use Greek letters for angles, so I'll call this angle alpha. And in that case, the side that's across from the angle alpha is called the opposite side, and the side that is next to the alpha, the leg, is called the adjacent. Okay, so what we're going to do is define a trig function. So a trig function is going to be a function of the angle. In this case, I'm going to do it for the angle alpha. Now there are 6 trig functions, and I'll just list them out here. So we have sine, and then as a function it's abbreviated sin, S-I-N. So sine is the name, and mathematically we would just write sin of alpha. To go with that, we have cosine, and that's cos of alpha. And then there are 4 more. So we have tangent, and that is abbreviated tan of alpha. And then there are 3 more to go with it, one called cosecant, and that's C-O-S-E-C-A-N-T, and that's abbreviated CSC, so it's CSC of alpha. And then there is secant, and that's abbreviated SEC of alpha. And then we have cotangent, and that is cotangent, COT of alpha. Okay, now how are these functions defined? Well, we'll start with the 3 that are on the top, and actually there's really only 2 that need to be defined, and all the others can be understood in terms of them. So we'll start with sine. Sine of alpha, and I'm going to keep using the red for alpha because I still want to refer to this triangle, is defined to be the opposite side over the hypotenuse. And then cosine alpha, oops, I'll do that one in red still, is defined to be the adjacent side over the hypotenuse. And then lastly, we need tangent of, and actually let me put parentheses around all of these guys just to be clear. So tangent of alpha is defined to be the opposite over the adjacent. Okay, so those are the definitions of those three, and then the thing that's neat about the other ones is that they're actually just reciprocals. So, for example, cosecant is 1 over sine, and because sine is opposite of our hypotenuse, the reciprocal of that is the hypotenuse over the opposite. So I'll just abbreviate it like that. Similarly, secant is the hypotenuse over the adjacent, and cotangent is the adjacent over the hypotenuse. So figuring out cosecant, secant, and cotangent is really easy. You just figure out sine, cosine, and tangent, and then flip them over. One other thing that you could notice is that tangent is actually the same thing as sine over cosine. And the reason this is the case is because sine alpha is opposite over hypotenuse. Cosine alpha is adjacent over hypotenuse. And now we've got one fraction divided by the other. So we flip the bottom one and multiply. And then you notice here that in the fraction we've got the hypotenuse both in the numerator and the denominator, so we can cancel that, and we get opposite over adjacent, which is exactly what we defined to be tangent. Okay, so this proves to us that tangent is in fact sine over cosine. Okay, so in the next segment we'll look at with some specific numbers here, how you compute these. Okay, so let's look at this for a specific triangle that's actually got some numbers. So I've kind of cooked the numbers on this one deliberately so that we get nice answers. So I'm going to take a right triangle, and again we'll go ahead and put this alpha right, oops, I want that to be curvy, alpha right there. And in this case, I'll take the triangle to have dimensions 8 on this edge, 15 on this edge, so I know it's really out of scale, and then 17 on the hypotenuse. So the reason I picked these is because, of course, since this is a right triangle, we know that 8 squared plus 15 squared should equal whatever the square is on this side, and it just so happens that that's 17 squared. So I picked the numbers so that both Pythagoras' theorem would work out, and they would all be whole numbers just for convenience. Okay, so let's figure out the value of the 6 trig functions for this particular angle, alpha. So let's start with sine. And what we said in the last segment was that sine was the opposite side over the hypotenuse, and so that's 8 over 17. And this is exactly what it is. So if you wanted decimal approximation, you'd actually do the division here. It'd be kind of ugly because of the division by 17, but that's it. And then similarly, cosine of alpha is the adjacent over the hypotenuse. And tangent of alpha is the opposite over the adjacent, so that would be 8 over 15. And then the three other ones, sine goes with cosecant, and I'm really sorry that that's the way we've named them. It would make more sense for sine and secant and cosecant to go together, but that's not the way it is, sorry. Anyway, so cosecant of alpha is just the reciprocal of sine, so that's 17/8. All I did was flip this one over, and then ditto here. Secant of alpha is 17/15, just the reciprocal of cosine, and then cotangent of alpha is 15 over 8. And so if you know all three sides of the triangle, it's actually pretty easy. If you only know two sides of the triangle, then you can use Pythagoras' theorem, which you probably remember in this form, just that, and C is always the hypotenuse, and then A and B are the two legs. Okay, so now in the next little short segment, we'll look at another example of this that's a little bit of a special case, and where we'll actually know also what the angle is. So in this example, we have no idea what alpha is. So here in my picture, it looks like maybe roughly a 30-degree angle, but we don't actually have a numerical measure for what that angle is. So in the next example, we'll actually know what the angles are. Okay, so for the last example, we'll look at a very special case of a right triangle, namely an isosceles one. So I'm going to consider a right triangle whose two legs are actually the same length, and my picture gets close enough. Okay, so now the neat thing about trigonometry is it actually doesn't matter how big the triangle is. The values of the trig functions of any of these angles sort of scale up and down, or well, since both the hypotenuse and the sides all scale up in the exact same way, when you form a fraction, the trig function actually doesn't scale up at all. So it doesn't matter how big how big the triangle is, the trig functions are always going to come out to be the same. So in this case, I'm going to just call that x for whatever the length of that is. And then what I'm going to show you is that the value of x actually won't matter at all, provided it's non-zero, of course. Okay, so if I'm going to consider an isosceles triangle, then I know that the other side is also x. Okay, so this is a very special case. Isosceles triangle. Okay, and then Pythagoras' theorem actually gives me that the other side here needs to satisfy this. So let's call this side y for right now because we don't know what it is. So this x squared plus that x squared should equal y squared. And so y squared equals 2x squared. And so y equals x square roots of 2. Okay. Okay, so I've got that. And now one other thing that we can mention here is what the actual values of these angles are. So if it's isosceles, one thing you may remember from geometry is that if the side of a triangle is the same as another side of the triangle, then the two angles that are across from them also are the same. So that means that this angle over here and the blue angle up there are actually the same in size. Okay, so isosceles implies that the red angle equals the blue angle. And if we think about this for a minute, based on some other knowledge from geometry, we also know that, well, actually here, why don't we label these things? So why don't we call this one alpha and that one beta, and then the right angle we'll just call gamma. So we know that in any triangle, the angles add up to a very specific number, and that number is 180 degrees. So you may remember this from geometry. Now, in our case, gamma is 90, and alpha and beta are the same thing. So for the isosceles case, we know that alpha plus alpha, because remember beta and alpha are actually the same number, plus 90 needs to equal 180. And the right angle is, of course, has a value of 90. And so what we get is twice alpha equals 90 degrees, and so alpha is actually 45 degrees. And that probably doesn't surprise you, particularly if you've done carpentry or something like that, where you've worked with a t-square like this. Okay, so now that we have the actual numerical value of this angle, we don't actually need that to figure out what the trig functions are, but what this will tell us is what the trig functions at 45 degrees are. So sine of 45 degrees we can actually just read off. It's whatever the opposite side is, which we don't know the length, we just called it x, divided by the hypotenuse is, and that in this case is x root 2. And this is where I told you that the actual lengths of the side doesn't matter, or don't matter, because notice what's going to happen to the x's. They actually cancel, and so what we get is just 1 divided by the square root of 2. Now, in high school, you may have been taught that you weren't allowed to leave square roots in the bottom, and if you really get bent out of shape about that, you can always just rationalize by multiplying by this, and in that case you get this number. But they're the same thing. Similarly, cosine of 45 is the adjacent over the hypotenuse. But by dumb luck, in this case, the adjacent and the hypotenuse, or excuse me, the opposite are the same, and so we actually get the exact same answer for this one. That's kind of special. Normally that doesn't happen, but it did in this case. And then lastly, tangent of 45 is the opposite over the adjacent, so x over x, which is 1. Okay, so in class what we'll do is look at another special triangle, not this one, but one that's a little different, and then start to build up how we can actually use this to solve problems.